This is the second part of the course dedicated to machine learning for omics data. In this part, we will train and compare several classifiers to predict leukemia diagnosis. From the first part of this course, we know how to prepare omics data for machine learning. A typical pipeline for data preparation is shown on this slide. If you don't remember why we need to apply all these steps, please watch the first part of the video. Let's return now to the example of leukemia dataset and let's train some classifiers for leukemia type prediction. The first classifier that I would like to show you is a logistic regression. The classical logistic regression is designed to classify samples between two groups only, but we can easily extend the method for several groups. How it works? Let's imagine that we need to detect samples of acute myeloid leukemia against other types. We use samples from a training dataset. Samples of acute myeloid leukemia are presented in red color. For these points, the probability to be acute myeloid leukemia is equal to 1. The probability is shown on y-axis and the expression level on x-axis. In our example, we imagine that the expression level of acute myeloid leukemia is rather high compared to other leukemia types, which are presented in blue. For these blue samples, the probability to be acute myeloid leukemia is equal to 0. In the logistic regression, we use a mathematical function called logistic function or C-shaped curve or also sigmoid function. Training a logistic regression consists to fit this particular analytical function to our data. It means that we need to optimize the position of the function and its curvature. For example, we can shift the function to the right or to the left, or change its slope in order to minimize the residuals between the curve and the real data points. When the curve is correctly placed, then we can proceed to predictions on new samples. For a new sample, we project the expression level of the sample on the logistic curve. The corresponding value on y-axis will give us the probability for the sample to be acute myeloid leukemia. In this case, the probability is equal to 80%. Usually, we put a threshold between groups at 50%. All samples above 50% of probability will be classified as acute myeloid leukemia. The logistic regression for multiple classes is very similar. We train a separate logistic regression for each class against others, and we compare the obtained probabilities and we select the class with the highest probability as a final prediction. Training logistic regression in Python is rather straightforward. First, we create a classifier, logistic regression, with some options. Especially, we need to precise that our data have more than two classes, with multi-class option equal to multinomial. We don't use here any regularization, either ridge lasso or elastic net. Therefore, the regularization, which is also called penalization, is set to none. A regularization is usually applied to better constrain the model and to avoid possible overfitting. It's a very common technique, a good practice, so common now that it's included by default in almost all the classifiers in scikit-learn framework. If you don't want to use it, then we need to explicitly precise it in options. The last option, solver, indicates which numerical method should be used to minimize residuals to fit the logistic curve to the data points. Many solvers are available in scikit-learn. Here I choose Newton conjugate gradient method. Next, we train the classifier with fit method on the training dataset, which has been already scaled. Then we can predict labels for new samples using predict method on the test dataset. Finally, we can calculate the prediction accuracy comparing real labels with predicted labels on the test dataset. One of the advantages to use a dedicated framework as scikit-learn is that all the classifiers implement the same interface. It means that all the classifiers will have fit and predict methods. Therefore, if we want to change the classifier, for example, to use a neural network instead of the logistic regression, we need to change only one line in our code, just the line where we create the classifier. We don't need to change the rest of the code. The other lines will work perfectly independently on the selected classifier. This is the prediction accuracy obtained by logistic regression on leukemia dataset. As you can see, we can calculate the accuracy in training dataset, in test dataset, and in leave-out dataset. The results in training and test datasets correspond to a cross-validation in our pipeline. Inside the cross-validation, we train the logistic regression on a training dataset, and then we test it on a test dataset for each iteration, in total 3 times. We calculate 3 values of accuracy corresponding to each iteration of cross-validation, and then we plot the average values. On the figure, we can see that the accuracy in training dataset is always perfect, 100%, for all the 3 iterations. In test datasets, the accuracy changes slightly. In average, we obtain 98.6%. These values allow us to evaluate the performance of our model. We have a very slight overfitting because the accuracy in training dataset is a little bit higher than in test dataset. Nevertheless, the difference is really small, so we can accept it. In the last step, we retrain the logistic regression on the entire initial training dataset, and then we apply it to leave-out dataset for final prediction. As expected, we currently predict 98% of samples. It means that the prediction fails for 2 samples. It can be interesting to see where the prediction failed. This figure shows a principal component analysis for the leave-out dataset. We have 100 samples in total in this dataset. The crosses show where we have a bad prediction. The cross on a blue point means that the real sample is acute lymphoblastic leukemia, while our prediction classified it in acute myeloid leukemia. The situation is just opposite for the second error. The cross on a red point means that the real sample is acute myeloid leukemia, but we predicted it as acute lymphoblastic leukemia. As we can see, both arrows are placed near the boundary between 2 classes. It's a little bit difficult for our classifier. For the third class, chronic lymphocytic leukemia, the prediction is just perfect. This class is well separated from the others, and our classifier performs very well. Another widely used classifier that I would like to show you is called support vector machine, or SVM. This classifier is linear in its classical form, but it may also perform a non-linear classification. How it works? The SVM method tries to place a boundary between 2 or more classes. In a general case, there are many solutions to put such a boundary, just to put a straight line. But the SVM method feeds the data to find a unique boundary that maximizes the margin between the boundary and a few closest samples of each class. These closest samples are called support vectors. That's why the name of the method is support vector machine. When a boundary is defined from the training dataset, then a new sample can be easily classified depending where it's placed with respect to the boundary. The results obtained with the linear SVM method for our leukemia dataset are very similar to those of the logistic regression, so I don't show here these results. It's more interesting for us to try a non-linear version of the SVM method to see if we can improve the prediction. The SVM method can perform a non-linear classification if we use a kernel trick. It's a modified version of the method. A kernel allows us to bend the boundary, which will be no more a straight line, but can take different forms. For example, with RBF kernel, RBF means radial basis function. We can achieve more rounded shapes of the boundary. Let's use it in our example. But other kernels are also available and different shapes are possible. To train the SVM classifier with RBF kernel, we need to choose 2 hyperparameters. The first parameter, C, controls the degree of regularization to avoid overfitting. As we already discussed, the regularization is a good practice and it is included by default in scikit-learn for many classifiers. For the SVM method, we will use a standard ridge regularization. The second parameter, gamma, controls how strong we bend the boundary while using kernel. Do we need a very rounded shape of the boundary or almost a straight line? At this stage, we don't know what values to put for these parameters. We don't know what values are appropriate for our problem and for our dataset. When the dataset is not very big, as in our case, we can try a so-called grid search for hyperparameters. It means that we just try several values for each hyperparameter, and see which values are optimal. In this example, I tried 10 different values for the parameter C and 6 values for the parameter gamma. For each couple of parameters, I train the model and then I measure its mean accuracy in test datasets using cross-validation. We can see that for some parameters, the accuracy is poor, essentially when gamma is high. The accuracy in this case is only 43%. It means that the shape of the boundary is bended too strongly and doesn't fit the data well. On the contrary, for other parameters, we obtain a good prediction accuracy. Finally, we can select a pair of hyperparameters that gives the best possible accuracy in test datasets. Now, let's see how our model performs. We obtain the accuracy of 100% in the training dataset and the accuracy of almost 99% in the test dataset. In the leave-out dataset, we are able to correctly predict all the samples except one. Yes, the nonlinear SVM model performs a little bit better than the logistic regression. We gain it 1 point. Of course, the difference is not huge because the logistic regression performed already very well, but this new nonlinear model seems to be even better. Nowadays, neural networks, deep learning, are very popular in data analysis and in precision oncology in particular. It could be interesting to train a neural network for our leukemia classification use case and to compare with other methods. I will introduce here the main idea of a basic neural network. If you need more details, please check the excellent MIT course Introduction to Deep Learning, publicly available on YouTube. Highly recommended. I will use some slides of this course to briefly explain what a neural network is. A classical neural network is composed of several interconnected artificial neurons, which are called perceptrons. The concept of a perceptron is rather simple. It's similar to a logistic regression. On the figure, x1, x2, xm represent expression levels for genes 1, 2, m, and a bias. In the first step, we calculate the weighted sum of all the expression levels. We obtain as a sum just one value. In the second step, we apply an activation function on the sum. For example, the activation function could be the sigmoid function that we have already seen in the logistic regression, and that allows us to transform the sum of expression levels to a probability. For example, the probability that the sample is acute myeloid leukemia. If we use the sigmoid activation function, we obtain exactly a logistic regression. The mathematical formula will be the same, but in the case of a perceptron, it's possible to choose other activation functions, not only the sigmoid function. We can say that a perceptron represents a generalization of the logistic regression. We would like to create a neural network with building blocks which are perceptrons. For this purpose, we should put several perceptrons in communication. How to achieve this? On this figure, we can see a single perceptron with a simplified representation. It is the same as on the previous slide, just in a more compact representation. This perceptron has a single output. Let's add a second output. This figure corresponds to two logistic regressions, which are trained separately. For example, the first output could correspond to the probability for a sample to be acute myeloid leukemia, and the second output to acute lymphocytic leukemia. For the moment, the outputs are not interconnected. We can now interconnect outputs to obtain a full nonlinear neural network. More precisely, we deal here with a simple classical architecture of neural networks, which is called a multilayer perceptron. It exists many other architectures that aim different problems. In a neural network, we usually have several internal layers that are called hidden layers. We have also inputs, which are initial expression levels, and outputs, which are, for example, probabilities of different types of leukemia. We can increase the number of hidden layers. The number of nodes in each hidden layer could be different. In this example, we have two hidden layers with 4 nodes in each, but it could be, for example, 10 nodes in the first hidden layer and 20 nodes in the second hidden layer. Of course, the number of hidden layers can be much more important. In scikit-learn, we can train easily a multi-layer perceptron as any other classifier. We just need to replace the line where we create a classifier. Here we can create a multi-layer perceptron with some parameters. I use the early stopping technique to avoid memorization of data and to avoid overfitting. Our neural network will have 4 hidden layers with 100 nodes in each layer. And we will use a ridge regularization controlled by the parameter alpha. The other lines in the code are exactly the same as for previous classifiers, logistic regression or SVM. Here are the results obtained with this neural network on Leukemia dataset. As for the SVM model, we predict correctly almost all the samples in the live-out dataset except one. Nevertheless, this model is preferable to the previous SVM model because the overfitting here is low. The accuracies in the training and test dataset are very close, as you can see. Still, the prediction fails on the same point in the live-out dataset. With real-life datasets, we can barely expect a perfect prediction, 100% in all the cases. So, this result is very satisfactory. To conclude, we learned today that the analysis of mixed data with artificial intelligence approaches may be challenging. The first challenge is that the results obtained in one study may potentially not be confirmed in another one due to possible overfitting problem. Therefore, when we train an AI algorithm, we need to pay special attention to overfitting in order to obtain robust results. A cross-validation would be a good practice in this situation. Then we considered a problem related to a very important number of parameters in mixed data compared to a relatively small number of samples. This problem may also result in artifacts and overfitting. We have seen that many possible solutions are available, for example, selection of parameters or regularization techniques. We also learned that the data should be scaled, otherwise some machine learning algorithms may not converge very well. And finally, we saw some examples how to train linear and non-linear models for leukemia classification and how to choose hyperparameters with a grid search. So thank you for your attention and good luck with your projects.